So we'll look and see how Hessenberg's theorem goes. This is theorem 426 in the notes. Hessenberg's theorem. So let kappa be an infinite cardinal. Here. So kappa is greater than or equal to omega. As I used to say to my 12-year-old daughter when she was trying to get me to do her long divisions in school, I don't do finite. Here we're only interested in really what happens for infinite cardinals. For finite cardinals, everything is just what we know already about arithmetic. So there is a bijection between kappa cross kappa and kappa. Right? So kappa cross kappa is bijective with kappa. So that means, just translating that into this is times Cartesian product, kappa cross kappa. So that means, so kappa times kappa, size of this Cartesian product, that's kappa. So from this, actually, we get a number of corollaries, right, about cardinal arithmetic. So let's see how this goes. Now we know by induction on cardinals, okay, gamma greater than or equal to omega. We're interested in infinite cardinals. So we know already, we've already seen that omega cross omega is bijective with omega. Right? So that's our starting point here. So we'll assume that it holds for all infinite cardinals lambda less than kappa. So as inductive hypothesis, assume for if omega is between lambda and, sorry, if lambda is between omega and kappa, that lambda cross lambda is bijective with lambda. And we'll prove it for kappa. And what we do is look at a special ordering on this Cartesian product here. And it's called the Girdle Ordering. On kappa cross kappa, and it's a well order. And elements here are ordered pairs. So we're going to have alpha beta, and I'll call it the triangle order here. This is going to be less than gamma delta if and only if. We're going to order them first by maximum size. Right? So if the maximum of alpha beta is less than that of gamma delta, like that. Or maybe these maxima are the same, and then we'll have to do something else. Or and what are we going to do then, right? we're going to say, then it'll be like the no, then it'll just be like the alphabetical, lexicographic ordering. So alpha comes before gamma here, or alpha equals gamma and beta comes before delta here. So that there. So either the maximum of this pair is less than this, or the maxima are the same, in which case it's then the dictionary ordering. Alpha comes before gamma, or they're the same and beta comes before delta. And that's where we'll put this strictly before this, then here. So the first thing to worry about, is this really a well order? Okay. So here I'm picking ordinals less than kappa. I think I'll just leave you to find out that it's a strict total order. I mean, given any pairs, alpha, beta, gamma, delta from kappa cross kappa, it's one of these three things is going to happen. Right? So either one is going to be less than the other or the other way around. So this is exercise. We worry about whether it's a well order here. We show it is a well order. Okay, so what do we have to do? We take some non-empty subset of the field of the well order, X, and we need a triangle least element of X. So we want to show there's a triangle least element of X here. Well, we just look back at the ordering and say, okay, I'll just minimize. First of all, I'll see which pairs in X have got smallest maximum. And then all of those are the smallest maximum. I'll look at those which have got smallest first element. Right? And then all of those are the smallest first element. I'll see which ones of those, which one, single one, has the least second element. So in words, that was it. So let gamma 0, right, be the least of all of these possible maxima. Right, so I just look at the least possible maximum that's there. Right? And now I'll look at the things in X which have that least maximum. Right? These are the alpha betas in X, such that this maximum is this least value. And we let then alpha 0 to be the least first coordinate for the things in X0. So the minimum of the collection of alphas such that alpha beta is in X0 here. And similarly, we let beta 0 be the least thing so that alpha 0 beta is in X0. And then this alpha 0 beta is what we want. So this is triangle least here in X. So it's a well order. So let's give a little picture of what the well order looks like. Okay. So we're talking about things, pairs of ordinals inside the kind of box of kappa cross kappa. And so kappa cross kappa here. And okay, the least thing is 0, 0. Right? Obviously the least maximum, least first and second elements. Then if you think about what comes next, so here's 0, 0. The thing that comes next is 0, 1, okay, which is here. And then what comes next after that, something with the same maximum, 1, but actually it's this here. And then comes 1, 1, the corner of this box here. After that, we're involved in the 2s. It's 0, 2 up here. Then comes 1, 2. And then it hops down here to 2, 0. And it goes up the vertical, 2, 1, and then fills in the corner, 2, 2. And that's how it continues. It goes along the top, stops before the corner, and then goes up the vertical. And then finally finishes off the corner. So it's going to go through all the finites like this until we get up to, say, omega here and omega. So it fills in the omega cross omega box all the way through, horizontal, vertical, and so on. And then it's going to start across this horizontal here, 0 omega, and then 1 omega, here 2 omega, 3 omega, and so on. It'll fill in all of these. It'll stop before the corner, omega, omega, and go down to omega 1. Sorry, omega 0. And then it'll go up the vertical like this. And then finish the corner, omega, omega, at the end. Now, of course, omega may not be the only infinite cardinal less than kappa, but the picture continues then in exactly the same way. So this is how the triangle or girdle ordering here works. Right? And I'm going to use the result from the exercise that immediately precedes the theorem. Right? Okay. Each alpha beta here in kappa cross kappa How many predecessors has it got? Right. Well, it depends how big alpha and beta is. I mean, alpha could be 0 and beta could be large. But actually, so we look at the maximum of alpha and beta. Okay, the larger of these two here. And we add on 1 for safety's sake, for good measure here. Then what we've got, right, is that how many predecessors has this got? Well, if I'm looking in the, say I'm here inside the, maybe alpha is bigger than beta. Here, alpha's here and beta's here, perhaps alpha's over here. So I'm inside this box, right? I'm in, well, here's beta cross alpha. Here's the alpha cross alpha box, right? Like this. Yeah. So I've just supposed here that beta is less than alpha. So all the points that precede, right, alpha, beta, right, here, are inside this square here, or perhaps they're on the line, right? But in any case, if I add one more, they're all strictly inside this here, and okay, strictly inside this box, if alpha is the larger of the two. So alpha beta, right, here, its predecessors, all inside this box. So the size of the box is this maximum plus 1 here. So this square, this outer square here, has got this, it's this Cartesian product, and this is its size. Now the point is that, and when we appeal to the exercise, is that each of these boxes here is inside the kappa cross kappa box, right? Alpha and beta is an ordinal, these are both ordinals smaller than the cardinal kappa. So here, each of these has got size less than kappa. So this cardinality here is size, so it has no more than many predecessors. So the way I've drawn it shows, okay, alpha, beta doesn't have any more predecessors than what's in the alpha, alpha box here. 2 is saying that is less than kappa. 2 is saying that's less than kappa here. So look at the proof there of 2. Well, this is really kind of trying to write down what I've drawn there in this picture. So the triangle predecessors of alpha beta here fit inside a Cartesian product box of the sizes given. So if I were to think of this as an ordering, if A triangle is this ordering we're defining on kappa cross kappa, here, where A is kappa cross kappa, here. What I'm saying here is if I look at the initial segment determined by alpha beta, here, this is contained in gamma cross gamma, where gamma is this maximum plus 1. Okay, that was what I was trying to draw in the picture that's up there. Now, we made a remark earlier. Right? Okay, we said that the cardinality of this Cartesian product ends up as being this cardinal multiplication, gamma times gamma. And it's there in the notes. It's remark 4 above on the previous page. Okay. Okay, so the size of this box is just this Cartesian, sorry, this Cartesian box is the size of this cardinal product that's here. Right? But alpha and beta, and so gamma, are less than kappa. So this here is an infinite cardinal less than kappa. And the inductive hypothesis applies. So by the inductive hypothesis, this is gamma itself. And that's less than kappa. So that finishes 2 there. So by 2, we've got that the ordering here, the triangle ordering on kappa cross kappa, all of its initial segments have got size less than kappa. So the exercise before applies. So all initial segments of the kind I've been drawing have order type less than kappa. So by exercise, previous exercise, 424, right? The order type of the whole thing here is no greater than kappa. This is OT for order type. Is less than or equal to kappa. On the other hand, the order type is at least kappa because A is just kappa cross kappa. So this order type can't be smaller. Because it's got at least kappa things in it. So we have equality. So there's a one-to-one map from A, which is kappa cross kappa, with kappa. So in other words, A, which is kappa cross kappa, is bijective with kappa, which is what the theorem was after. So we've shown that if it holds for infinite cardinals less than kappa, it holds for the infinite cardinal kappa. Therefore, by principle of transfinite induction, it holds for all cardinals kappa. And that completes the proof of Hessenberg's theorem.